96% of organizations are using or evaluating Kubernetes. That is nearly universal adoption for a piece of infrastructure software. And yet, in the same surveys, 53 to 68% of those same organizations report that Kubernetes turned out to be more complex and more expensive than they expected. Not a little more expensive. The staffing and training costs in many cases exceeded what they saved on infrastructure. And here is the critical distinction. Adoption is not the same as satisfaction, and neither is the same as positive return on investment. The gap between those numbers is the story. This is no tech. To understand why this paradox exists, you have to go back to where Kubernetes came from. Around 2003, Google was running one of the largest computing operations on the planet. To manage that scale, they built internal systems called Borg and later Omega, container orchestration platforms that handled scheduling, resource allocation, and failure recovery across tens of thousands of machines. These systems worked because Google's scale demanded they work. But Borg and Omega were never public. They were internal tools, refined over more than a decade for a specific operational context that almost no other organization shared. Then, in June of 2014, roughly 11 years after Borg first ran internally, Google open-sourced Kubernetes. In 2016, the Cloud Native Computing Foundation accepted it as a founding project. The ecosystem accelerated. The pitch was compelling. Stop paying for idle servers. Let the scheduler pack your workloads tightly. When something fails, Kubernetes restarts it automatically. Scale up when traffic spikes, scale down when it drops. The narrative was clean. And by 2023, a 96% adoption figure seemed to confirm it. But there is a design tension buried in that history that rarely makes the conference talks. Kubernetes was designed around lessons learned at a scale most organizations will never reach. The architecture encoded assumptions about team size, workload volume, operational maturity that transfer well at large scale and transfer poorly at small scale. Adoption is a decision made at a moment in time. What happens after that decision is a different story entirely. Here is where the numbers stop being comfortable. 53 to 68% of organizations report that Kubernetes deployments are more complex and more costly to operate than they initially expected. That is not a fringe outcome. That is the majority experience. The most commonly cited hidden expense is not the infrastructure. It is the people. Running Kubernetes in production requires engineers who understand it at a deep level. Not just how to deploy a pod, but how to interpret a failing etcd consensus log, how to trace a kubelet eviction back to a misconfigured resource limit, how to debug a network policy that is silently dropping traffic. That expertise takes years to develop and costs real money to hire. For smaller teams, say 5 engineers managing fewer than 50 microservices, that cost frequently produces negative return on investment. The operational complexity does not shrink because your cluster is small. The control plane still needs etcd, an API server, a scheduler, and a controller manager, regardless of whether you are running 10 pods or 10,000. In 2023, David Heinemeier Hansson, the creator of Ruby on Rails and co-founder of 37 Signals, documented exactly this kind of outcome. His company left Kubernetes and saved $1.5 million annually. That is a real number from a real organization. It is also a workload-specific outcome. 37 Signals runs a particular scale profile with stateful components and a relatively small team. It is a data point, not a universal prescription. For a company running hundreds of stateless microservices across multiple regions with a dedicated platform team, the same calculation might look entirely different. The question is not whether Kubernetes is good or bad. The question is, good or bad for whom and at what scale? Let me walk you through 3 specific places where the Kubernetes promise collides with operational reality. Kubernetes bin packing can achieve 60 to 75% utilization of declared CPU requests, compared to 20 to 30% with traditional virtual machines. That is a genuine, documented scheduling efficiency gain, though, as we will see, declared requests and actual consumption are not the same number. But here is the part that does not make the conference talks. According to Datadog's 2023 State of Cloud Costs report, over 65% of Kubernetes workloads are over-provisioned, with CPU requests commonly set 3 to 4 times higher than actual sustained usage. This over-provisioning varies by workload type and team discipline. What does that look like in practice? A pod running an API server declares a request of 2,000 millicores. Its actual sustained usage is around 450. The scheduler sees the declaration, not the reality. It reserves 2,000 millicores of node capacity for a workload consuming less than a quarter of that. The Kube scheduler is doing exactly what it was designed to do. It packs pods efficiently based on what engineers tell it to expect. This is an important distinction. Orchestration overhead, the scheduler itself, etcd, the control plane, accounts for roughly 5 to 15% of resource waste in a typical cluster. The remaining 85 to 95% is human behavior. Engineers setting conservative resource requests as a buffer against uncertainty and never revisiting them. Kubernetes documentation, from version 1.19 onward, provides tools to address this. The vertical pod autoscaler, limit range objects, resource quotas at the namespace level. The tools exist. But Datadog's data shows that 65% of teams are not using them effectively, which means the efficiency gain on paper is substantially smaller in practice. The promise of autoscaling is elegant. Traffic spikes, Kubernetes notices, new capacity appears. The reality involves a timeline that matters enormously for certain workload types. When existing nodes are full, the horizontal pod autoscaler triggers the cluster autoscaler to provision a new node from the cloud provider. On AWS, that node provisioning process, from EC2 request to a node that is ready to schedule pods, takes 2 to 5 minutes. That is not a guess. That is documented in AWS EKS operational guidance. Pending, running, initializing, ready. During those 2 to 5 minutes, your traffic spike is happening right now. Requests are queuing or being dropped. Your autoscaler is working correctly. The capacity just has not arrived yet. Autoscaling does reduce idle capacity costs meaningfully, but it does not eliminate the gap between when demand spikes and when capacity arrives. For workloads with gradual, predictable traffic ramps, the autoscaler keeps pace. For workloads with sudden, unpredictable spikes, a viral moment, a scheduled batch job, a flash sale, that 2 to 5 minute window is a real operational risk, that requires explicit design choices, pre-warming nodes, maintaining buffer capacity, or implementing load-shedding strategies. Kubernetes uses namespaces to separate workloads. This is logical isolation, enforced at the API level. It is not hardware enforcement, and it is not the same as the isolation you get from separate virtual machines or separate cloud accounts. By default, a pod in one namespace can reach a pod in another namespace over the network. There is no firewall. There is no access control list. There is a naming boundary and nothing more. Network policies exist to restrict this. They are powerful and well documented, but they must be explicitly written, applied, and tested. They are not on by default. A new workload added to a cluster has no network isolation until someone deliberately configures it. In 2021, CVE 2021-25735, a kubelet privilege escalation vulnerability, demonstrated that node-level security policies could be bypassed when the kubelet's own enforcement logic was exploited. The vulnerability allowed an attacker with node-level access to escalate privileges by circumventing kubelet-enforced security checks.
This is a real security concern.
It shows that even explicitly configured pod security policies can be undermined at the node level, reinforcing why admission webhooks and network policies alone are insufficient as the sole security boundary in multi-tenant environments. None of this means Kubernetes is insecure by design. The security model is well documented and the tooling is mature. It means that isolation in Kubernetes is a configuration outcome, not a default state, and that layered controls, including RBAC, network policies, and pod security standards, are all required together. That distinction matters significantly in multi-tenant environments. So here is what the evidence actually shows. Kubernetes is not a cost reduction tool. It is a complexity trade. At large scale, hundreds of stateless microservices, dozens of engineers, workloads that are horizontally scalable, that trade is frequently favorable. The scheduling efficiency gains are real. At that scale, the staffing cost amortizes across enough workloads that the economics work. But for smaller teams, fewer than 5 engineers, fewer than 50 microservices, the same trade is often unfavorable. The operational complexity does not shrink. The fixed cost of the control plane does not shrink. And stateful workloads, databases, message queues, anything that needs to persist state across pod restarts, require explicit recovery orchestration on Kubernetes. Pod restart, persistent volume remounting, and application startup. That process typically takes 5 to 30 minutes, depending on application design and volume provisioning speed. AWS RDS Managed Failover, by contrast, handles replica promotion automatically within 60 to 120 seconds. These are fundamentally different operational models. One requires your team to design and own the recovery sequence. The other offloads it entirely to the managed service. For mission-critical, stateful workloads where sub-minute recovery time is a requirement, managed database services often provide stronger guarantees than self-managed Kubernetes stateful sets. And here is the number that ties this together. The CNCF data showing 96% adoption means 96% of organizations are either currently running Kubernetes or actively evaluating it. That is fundamentally different from satisfaction data, where 53 to 68% report unexpected complexity, or from ROI data, which the industry has not systematically measured. Adoption measures a decision. Satisfaction measures an outcome. Return on investment measures the economics over time. The industry narrative has been collapsing all three into the same number, and that collapse is where the paradox lives. So how do you actually evaluate whether Kubernetes makes sense for your situation? The honest answer is, start with the questions nobody asks in the pitch meeting. How many engineers do you have who can debug a failing etcd cluster at 2 in the morning? What percentage of your workloads are stateless and horizontally scalable versus stateful and session-dependent? What does your traffic pattern actually look like? Gradual ramps or sudden spikes that could expose that 2 to 5 minute auto-scaling gap? And critically, have you modeled the fully loaded cost, including the hiring and training investment, the on-call rotation, and the Kubernetes-specific debugging time that does not show up in your cloud bill? The 37 signals case is instructive precisely because it was honest about the workload profile. They ran a specific type of workload, smaller scale, with stateful components, and the economics did not favor the complexity. For a company running thousands of microservices across multiple regions, the same calculation maps to a different zone on the ROI curve. There is also an honest gap in what we know longitudinally. Comprehensive, peer-reviewed datasets tracking cluster utilization and total cost of ownership 12 to 24 months after adoption are limited. While practitioner case studies and vendor reports exist, standardized longitudinal data is scarce, leaving long-term Kubernetes economics genuinely uncertain for most organizations. The surveys we have are point-in-time, self-reported snapshots. The short-term efficiency gains are well documented. The sustained economics beyond the first year are not. What we do know is this:
The efficiency gains are real at scale. The hidden costs are real at every scale. The break-even point is not where the marketing says it is, and the tooling to close the gap, accurate resource requests, vertical pod autoscaler, namespace-level network policies, exists in the documentation. The gap between what Kubernetes can do and what most clusters actually achieve is not a Kubernetes problem. It is a configuration and operational discipline problem. Kubernetes reminds us that adoption is not validation. When a tool spreads fast enough, the question stops being whether to use it and starts being whether anyone is still asking if they should. But Kubernetes is not the only infrastructure decision that followed this arc, adopted at speed, understood only later. I'm here to help you know the systems running the world. If you've run Kubernetes in production, what was the cost that surprised you most? The staffing? The stateful workload recovery times? The over-provisioning you only found when you ran kubectl top? Share your experience below. The people watching this need real numbers, not marketing slides. See you at the next control plane.